Thank you so much for this opportunity. And so I will tell you about Bekenstein's area law. And there's a common wisdom that maybe Bekenstein's area law for the black hole entropy um, should be modified once you go beyond Einstein gravity. And so the aim of this talk is to actually tell you that maybe this is not the whole story, and maybe the story is a little bit more complicated. So what we laugh about the Bekenstein's area law is the following formula, and I would think that this is one of the most beautiful formulas in theoretical physics. And one of the reasons is that basically it combines all of theoretical physics. So it combines relativity, where you have the constant c. It combines the statistical physics because you have the Boltzmann constant in there. It combines quantum mechanics with gravity. So it's very, very, very beautiful. And moreover, it has very intuitive meaning. So if you actually introduce the Planck scale, as done over here, then you will see that your entropy formula rewrites as basically you measure the area of the black hole horizon in these Planck units square. And so that precisely tells you, like, yeah, I divide my horizon into small pieces, and how many of those pieces I have, that gives me the black hole entropy. Moreover, this formula is holographic, meaning that actually you would typically think that the entropy of a system should scale as the volume of the system. However, this is not the case for black holes. It actually scales rather as the area associated with the surrounding boundary of the region. But as I told you, the accepted wisdom is that no matter how beautiful this formula is, it will get corrected once you consider higher curvature corrections to Einstein gravity. And so there's a magic formula for how to calculate this entropy, and it's given by Walt's prescription. And what basically Walt showed you is that you can calculate the black hole entropy by calculating some local quantity associated, evaluated on the horizon of the black hole. You integrate that, and then you get the entropy. And what is amazing is that this quantity Q here is actually not a charge associated with the Killing vector, which is the horizon generator. And so this prescription actually gives you, for Einstein gravity, precisely, it gives you the area law as prescribed by Bekenstein. But if you consider standard high curvature gravities, it will give you something a little bit different. So let me give you an example. So let me consider the simplest possible, if you want, modification of Einstein gravity. So the action now is the Einstein-Hilbert action plus a Gauss Bonnet term. So what a Gauss Bonnet term is doing is that basically it's a quadratic in the curvature term, and the coefficients of these quadratic terms are precisely tuned. So you have really 1 times Riemann square minus 4 times Ricci square plus 1 times Ricci scalar square. And so there's something magic about this specific combination, is that although it seems that your Lagrangian contains second order derivatives of the metric, it still yields the second order equations of motion. So anyway, so now you may be interested, like what the Walt prescription gives you for this theory. And interestingly, if you are in dimensions greater than 4, it gives you modification of the Bekenstein's area law. It gives you area over 4, plus you have to integrate the Ricci scalar. This is the determinant of the metric on the horizon. But there is a correction due to the Ricci scalar on the horizon. So you no longer have Bekenstein's area law. However, even more interesting story actually happens in 4 dimensions. So in 4 dimensions, you can show that this Gauss Bonnet term here is actually topological. It means it's like a boundary term. And so if you have a boundary term adding to the action, it doesn't affect the equations of motion. So basically, this action in 4 dimensions still yields the standard Einstein equations. However, what you can show is that the entropy actually gets modified if you add this topological term, and that's been known from the end of 90s, from 90s. And in fact, the shift in the entropy is proportional. So it's given time alpha, which is the coupling constant of my Gauss Bonnet term, times the Euler characteristic of your manifold. So basically, that counts how many holes your manifold has, and it's a constant for a given manifold, unless you change the topology and stuff like that. And so there's a constant shift in the entropy due to this Gauss Bonnet term. However, this actually raises an interesting question. So let's say you collide two black holes and you start with a manifold with two holes. And then you collide them and you form one black hole, and so suddenly you have only one hole in your manifold. And in this way, in principle, this term will contribute in such a way that you can make, you can tune alpha so that your entropy in this process will actually decrease. And so this gives a possibility of violating the second law of thermodynamics. Anyway, so this is the truth. So now what we can do is that we can go. So this was like a sort of trivial for the Gauss Bonnet gravity, but you can formulate another one, which is like obtained by a singular limit of the higher dimensional Gauss Bonnet gravity. So what you do is that you start with your higher dimensional Gauss Bonnet gravity. And then you introduce a conformally rescale metric. So you rescale the metric by e to minus 2 phi, where phi is some scalar field. Of course, at this point, this is just a change of variables. There is nothing new here. And so you plug this into your Gauss Bonnet action and in your Gauss Bonnet term. And then what you do is that you expand around 4 dimensions. So you expand in epsilon, which is d minus 4. Okay, so now you have the following expansion. You have the absolute term, and then you have linear term in epsilon, and then you have quadratic terms, and so on. So we already know that the absolute term is precisely what we were obtaining by naive limit d goes to 4. So we obtain a topological Gauss Bonnet term, which does not affect equations of motion. So that's not interesting. But then you may be after the second term in the expansion, and you can call, well, why don't I take the second term to be my new theory of Gauss Bonnet gravity in 4 dimensions? Of course, in order to do that, you have to rescale the coupling constant alpha hat epsilon to alpha, and then this term really becomes finite, and that's what you will call a new theory. At the same time, of course, the absolute term blows up, but you can kill that by adding the corresponding counter term if you want to. Or you can just say it's still topological, no matter that it's multiplied by infinity, and zero it away. All right, so this is the resultant theory. And if you look at the theory, it has the scalar degree of freedom. So now you have suddenly scalar-tensor theory of gravity in 4 dimensions. We have the phi scalar field. You have still the Gauss Bonnet term over here. And then you have some very specific and ugly kinetic terms for the scalar field here. All right. And so people have studied what happens to black holes in this theory. And if you naively apply the Wald prescription for the entropy, you will find that, again, the area law is modified, and it's modified by the value of the scalar field on the horizon. The scalar field on the horizon, so the scalar field in the space-time, spherically symmetric space-time, black hole space-time, it behaves like a logarithm of R over L. So, of course, if you evaluate that on the horizon, it gives you a logarithm R plus over L correction to the area law entropy. And what remains here is the standard integral over the Gauss Bonnet term. So it gives you a constant. Okay, so it's basically a scalar field on the horizon times a constant coming from the Euler characteristic of the manifold. But this is a very exciting result, and many people were super excited about it, because now you have basically classical field theory, which gives you logarithmic corrections to the entropy, which typically are considered like quantum effects, right? So you get typically logarithmic corrections to entropy at the quantum level, but here you are just getting it from a classical solution of a classical field theory. And so people were very excited about that, and they said, well, this is like the right Lagrangian to play with if you want to capture some quantum corrections and so on. Anyway, what we are trying to say is that this is actually not completely correct. And the reason why this is not correct is that the theory which you have here is shift symmetric. Meaning, if I take my scalar field and change it by adding a constant, then of course what happens that all these kinetic terms here, they vanish because they just kill the constant. But here I have the original scalar field plus constant times g. Okay, but we know that constant times g is topological. It doesn't affect the equations of motion. So really, we have classical shift symmetry for this Lagrangian, and so we have to have exactly the same classical solutions. But what happens is that we already know that if we add constant times g, that modifies the entropy. It shifts the entropy by a constant. So you have classical symmetry, which, however, affects a physical quantity like the entropy. So that seems very, very strange. And so we thought, why don't we make this shift symmetry which is true for the equations of motion, already manifest at the level of the action. And to that, you notice that really your Gauss Bonnet term is like a total divergence of something. And so what you can do is that you can take this action here, write the G as nabla mu G mu, and you can integrate by parts, sort of, by adding this boundary term over here. So what happens is that basically it shifts the derivative from nabla mu G mu to the derivative of, so this should be the scalar field phi, plus the remaining kinetic terms which are over here. So this is the scalar field phi. So now you see that this action is manifestly symmetric, shift symmetric, because now I am differentiating my scalar field, which is not visible here, and then I have kinetic terms. So really the action already manifests this shift symmetry. Very good. And at the same time, it leads to the same equations of motion, because all we have done is that we have added a boundary term. So there's your action, and now we can again use wall prescription for the entropy. And surprise, surprise, what you will find is that the logarithmic term suddenly disappears, and you just recover the Bekenstein's area law. So of course, there's a price to pay for this, and if you want your first law to be satisfied, and the mass does not change, and you want still dm equals to TdS, you have to modify the temperature. And this is the corresponding modification of the temperature. So this is the Hawking temperature, and this is the factor I have to multiply my Hawking temperature to get the temperature which satisfies the first law. Okay, so this was true for this 4D Gauss Bonnet gravity, but what about the pure Gauss Bonnet gravity, let's say in 5 dimensions? No scalar field. Well, in 4D, I was trying to tell you that the Gauss Bonnet term can be written as a total divergence of something. Unfortunately, or fortunately, or maybe there's a reason for that, there is no covariant expression known for this G mu. So typically this G mu can be explicitly defined in terms of the Christoffel symbols and stuff like that, but that's not a covariant expression. However, if you have a killing vector in your spacetime, let's say psi mu, then there is a covariant expression due to Patmanabhan. And so you just take the Gauss Bonnet term, you differentiate with the Riemann tensor, and then you take this combination of the killing vector and the d of killing vector, and that gives you the G mu. That's the prescription for this G mu. So that's a prescription for 4D, right? But why don't I use the same prescription for 5D? It's just an educated guess. So why don't I consider the 5-dimensional Gauss Bonnet gravity, which definitely leads to modified entropy, and then add this boundary term to it, okay? And if you do that and turn on the machine again, you find that the wall entropy formula gives you suddenly area over 4. It kills the modification of the entropy. Again, you have to modify the temperature. So where does this temperature come from, or is there a way to derive this modified temperature? And yes, there is. It's almost the standard Euclidean path integral formulation. It's a little bit twisted by Brown and York, and I can give you a reference if you are interested in. But basically, there is a Euclidean action calculation which allows you to derive the temperature of the space-time, and it precisely gives you this modified temperature, and it gives you this modified entropy. So you may be asking, like, why the temperature should be modified, right? It shouldn't be modified. It should be the standard Hawking temperature. After all we need is, it's thought that the Hawking temperature is just a kinematic effect. All you need is the existence of horizons. You need quantum fluctuations of fields and stuff like that. It shouldn't matter what kind of dynamical gravity theory you're considering. However, there are at least 3 reasons why maybe this is not the whole story, and why maybe the temperature could be modified. So first of all, there is an argument by Liberati and collaborators that maybe in certain theories, high curvature theories, actually the gravitons move differently than other particles, and they not necessarily move with the speed of light. They have some kind of birefringence and stuff like that. Well, of course, the speed of gravitons enters the temperature formula. So maybe it's because the gravitons actually propagate differently in these theories. The other one is that maybe in these theories, like as the particles propagate from horizon to infinity, you get some weird screening effect due to nonlinearities in the field or interaction with the scalar field or whatsoever. And actually, this is this reason actually might be true because that's precisely what this Brown and York procedure actually is suggesting. So it sort of calculates like what the temperature is as you move away from the horizon, and you see that the temperature is really modifying from the standard Hawking temperature as you would expect. Finally, what is the possibility is that we have added some boundary terms, right? And typically adding boundary terms corresponds to considering a different thermodynamic ensemble. And so maybe by adding these weird boundary terms, we have actually changed the thermodynamic ensemble. Maybe no longer we have really interpretation of temperature, or some weird things can happen. So anyway, so if you are interested to learn more about this, please look up our paper, which is by myself and Marek Liška, who is an amazing PhD student at Charles University. And also we have a follow-up, much longer paper, also with Robbie Henniger. So please. That's it. And if you have any questions, please ask me.
Amazing. Thank you, David.